Daniel.
And I'm Billy, and we're from the Google Cloud Developer Relations team. Our focus is on storage, and especially cloud-based storage.
We want to help you make informed decisions about what storage solution to use for your IoT project. We're going to start off by discussing a little bit about the shape, size, and scale of the data. Every industry has unique data problems, and we're going to focus on the kinds of problems that you might see when building IoT apps at scale.
Then we'll see why the cloud is a great fit for data of this shape and scale. And we'll look at how to ingest your data into the cloud.
We look into a number of storage characteristics that you need to take into consideration when reasoning about storage solutions.
And finally, we'll examine a few common use cases and real-world scenarios that businesses encounter. We'll map those business needs to technical storage requirements and then select a database based on that information. And we've got a few cool demos for you to check out today.
So this is a storage talk, although with a little bit of a cloud twist. And one of the first things to come to mind that comes to mind when we think about storage is, how much data can I store? This is a relevant question, especially in the, with an IoT use case in mind. Connected devices today produce massive amounts of data. According to Statista, there will be 50 billion connected devices by 2023. So this is a map of oil and gas fields in the Gulf of Mexico. Let's do a thought experiment. Let's say that we have 1,300 oil and gas fields, and each oil and gas field has 1,000 sensors streaming data. Even if those devices is only streaming 100 bytes per second, that still makes 137 megabytes per second in total, or over 8 gigabytes per minute, or 11.5 terabytes a day. You could try to manage that infrastructure on your own, but there's a reason the cloud exists. All the infrastructure headaches that comes with managing massive amounts of data is minimized by using the cloud. So let's make sure we are on the same page here when we talk about IoT data. What we really mean when we talk about IoT data is time series data. Some of the common requirements for storing time series data include robustness. For some applications, data loss simply cannot happen. We want high volumes reads and writes, and we want low latency to go with these high volumes of reads and writes. We want to have efficient ways of backfill historical data, and we want efficient sequential reads. The connected devices, the producers of the data we are talking about, could be anything from smart home appliances to public transit cards. Whether you're starting with 10 devices or 10,000, using the cloud to manage your devices, storage, and analytical tooling provides security, reliability, and scale. I will now hand it over to Billy, and he will talk a little bit about Cloud IoT Core.
Cool, thanks, Daniel. So yeah, our cloud-based solution for this is IoT Core. And you get secure connections, easy ways to manage your devices, and all of this is at global scale. We've got IoT Core, and then this breaks down into registries, which are the buckets that hold your individual devices. From there, the registries will automatically connect and publish messages to a Cloud Pub Sub topic. And Cloud Pub Sub is our event stream manager that will allow your IoT pipelines to scale. You get fine-grained access controls, end-to-end encryption, and at least once delivery to ensure reliable and secure streaming of data in a fully managed service. And all of this is global by default. Publish from anywhere in the world and consume from anywhere. With consistent latency, no replication is necessary. From there, PubSub integrates perfectly with Cloud Dataflow, our fully managed stream and batch data processing tool. And you can use this with the open source Apache Beam SDK. You can subscribe to the PubSub topic and then run your ETL operations on these messages. So this is our IoT pipeline so far. Set up your devices on IoT Core. They'll send messages to PubSub, and then your Dataflow job will process it. It works great with a handful of devices and scales up to handle 1,000 megabytes per second. If we think back to the example Daniel just showed of those oil and gas fields around the Gulf of Mexico, those are that could only produce around 15% of what this can handle. So this pipeline can really handle a lot, just to kind of give you that idea for scale. So we'll take the standard IoT pipeline, and then this is the part where you need to make a decision, choosing a storage solution for your data. Every database has strengths, and you have to make trade-offs to ensure you're using the database best fit for your use case. Daniel's going to talk about the features you'll find in various databases and what kinds of limitations you might run into as well. All right, here you go.
Thank you, Billy. As Billy showed in the previous slide, the ingestion pipeline is pretty standardized. The moving part here is storage. So in this section, we'll talk a little bit about the different characteristics that databases might have. Databases that, on the surface, will look pretty similar. So if this is too basic for some of you, we apologize for that, but we think it's important that everybody is on the same page before moving on. So we tried to group the deciding factors for your storage solution into 3 pillars. Functionality, such as data model, query languages, partitioning, etc. Scalability, which in the IoT world always will be a deciding factor. And lastly, cost. Let's see if this makes sense to you. So there are many types of data models. Just look at how many books there are on data normalization or stuff like that. And every data model comes with assumptions about how it's going to be used. Since the data model has such a profound effect on what the application can do or cannot do, it's super important to choose one that is appropriate for your use case. A good practice is to lay out the queries that you want to be able to perform on your data ahead of time. That will give you great insights in what data model to use. The relational model does a very good job of hiding implementation details behind a clean interface. However, the use cases we are looking at, other data models might be a much better fit. Let me give you a few examples. So we usually need greater scalability than what relational databases easily can achieve, especially when it comes to very large data sets or very high write throughput. A desire for more flexible schema design or a more expressive data model. For example, schema on read instead of schema on write. So many people feel that a declarative language like SQL is much easier to work with than an imperative one like JavaScript. And as we discussed previously, the relational model and subsequently SQL does a really good job of hiding implementation details of the database engine. So that means that the database vendor can introduce performance improvements under the hood without you having to change any of your queries. On the other hand, many non-relational databases support specialized query operations that might fit our use case much, much better. One example would be efficient sequential reads. In a distributed system, or first we might just address the terminological confusion that this is all the same things, it's just what different databases call sharding or partitioning or regions or tablets and whatnot. But in a distributed system, data will always be partitioned. So when you have a system with data partitioned over several nodes, how will you go about scaling your cluster up and down as more nodes get added to the cluster? Will the database help you reassign data to new nodes, or is that something that you have to manage yourself? And if you have to manage it yourself, will that make you have to compromise on your scalability goals? In some systems, assigning ownership of a partition to a new node is an online metadata operation that doesn't require any any data motion. Spoiler alert, I think Billy will talk about one of these systems in a little bit. So, replication. Replication basically means that we are keeping a copy of the same data on multiple nodes. or multiple machines. There are several reasons why you might like your data replicated. So for once, you maybe want to make sure that your data is geographically close to your users. Another one could be for high availability reasons. Maybe you want to increase your throughput by adding additional read replicas. Or maybe you want to do it for workload separation. You might have one cluster serving data and an identical cluster for your analytical workloads. And lastly, cost. So how is the database licensed? Is it open source? Does the provider charge you for the amount of data that you store, or for the throughput that you get, or something else? Is it a managed service? Do you need to take on management and monitoring of the database? And if so, how do you quantify that cost? What does support cost? Do you have the competence for this technology in-house, or do you need to train people on it? We did it. Hopefully we're on the same page now and have a common language. So if there's one thing we want you to take away from this session, it is don't treat storage as an afterthought. So we've identified two different IoT use cases. The first one we call complex application logic. This is where the read-to-write ratio is balanced. These applications are not just about receiving data from the devices, but also controlling the devices. So the complex application logic is used to determine some kind of change that needs to be performed on the device. The other type of application that we've identified is something we call data ingestion intensive. Here we have many devices sending a lot of data upstream. These applications are write intensive as opposed to read intensive, and they are usually used for monitoring or analytics. With that said, let's look at a few scenarios. The first scenario, we will look at a newly founded IoT startup. The IoT startup is still in the beginning of their journey, so the team is still small. They have developed a platform for smart home appliances like light bulbs, thermostats, smoke detectors, etc. The data from each smart home appliance is very suitable to be stored as a self-contained document. And the smart home appliances are being controlled by mobile apps. So a family, for example, can have several mobile apps that are controlling these appliances. So let's map this to technical features then. Small team and limited resources. Most companies would probably benefit from serverless today, but for a small startup, it might be absolutely crucial. If you have a small team of developers, letting them focus on your core business instead of managing servers could make all the difference. Self-contained documents sounds like something that would be a good fit for a document database. The hierarchical structure lends itself to good data locality. And the fact that there is mobile apps that are being used to control the appliances gives us a hint that this is a complex application logic case. So this would be closer to the first of the two use cases we discussed earlier. So this startup, they don't only face the challenges of IoT. They also have to manage mobile apps. So let's have a quick look what it would take to build a mobile database the hard way. First, you need a database servers like MySQL, Postgres, or Mongo. And you got to manage and scale that database yourself. Then you want to query the database from afar, so you need an API layer. And that API layer needs to be able to authenticate and authorize your queries. And finally, you need to keep state locally, and that requires yet another database. And that database has to be kept in sync with a remote one. So that's a lot of stuff to do, and that's only to fetch some simple data. And I mean, let's not even get started on what it would take to make that a real-time system instead of a polling one. Let's see how we can simplify this. Enter Firestore. How many in here are familiar with Firestore? That's pretty good. So Firestore is what we call a serverless database. So a serverless doesn't mean that there are no servers. What it means is that everything from capacity planning, upgrades, maintenance, all of that is handled seamlessly by the system without scheduled downtime. Multi-region replication will keep your app and user data safe, available across regions in case of disaster without any configuration on your side. Firestore is a globally distributed database that will scale based on your usage. Cloud Firestore lets us structure our data as collection and documents, which makes queries much easier. We can store related data together in hierarchies. We based this model on what we learned from Firebase real-time database developers. We studied how people wanted to model their data, supporting the most common use cases with patterns that most developers designed intuitively. So far, we noticed that this reduces the learning curve and that the data model is designed to scale. Let's look at Firestore in action. So can we switch to the demo, please? This is actually super good. This is a live demo, but we have the creator of the demo in the audience. So if stuff goes sideways, you know. So we have 4 quadrants here forming the Firebase logo. And then we have 40,000 clients that we have simulated. And all these 10,000 clients are assigned to each of the quadrants. So what we'll do here is that all these 10,000 clients, they are listening to one of these inputs. So, and of course, so that no one will get upset, we do zero-based indexing here. So this is 0, this is 1, this is 2, and this is 3. So 10,000 is listening to each of these 4 documents. When they see a change, they will then write that change back into this collection, which is called pixels. And these are then 40,000 different documents. So when we do a change on one of the documents over here, that will trigger 10,000 reads and 10,000 reads from one document and 10,000 writes to different documents. And hopefully, it will also change the color of this. So if we take this one, and we change the color like this to red, and now it should. There you go. So we can change it back like this. Boom. And if you think this is fake, then we can actually look at the different pixels here. So let's switch it back to red again. And now you have to be focused because it will just flicker. There you go. Thank you, thank you, thank you. We can go back to the presentation. Thank you. And with that, I'll... oh, wait. So this sounds amazing, right? Firestore. So why would anyone choose another database over Firestore? Maybe Billy can help us answer that.
Yeah. All right, thanks, Daniel. Good demo. Glad it worked. So yeah, all this does look really good. But if you are in, so that's for the first case where it's complex logic. But if you're maybe more in the data ingestion intensive examples of a use case for IoT, you might need a different solution. So I've got a few examples for us to look at that have massive QPS requirements and solutions that are going to work for them. The first we're going to take a look at is for fleet monitoring using IoT. So let's say we are an enterprise scale company that wants to put some kind of monitoring device in a fleet of cars or trucks. We'd like to have a dashboard to monitor our fleet in real time so we could detect anomalies and provide feedback to the drivers. We'd also like to do the same with the historical data, store that in the database and potentially do machine learning on it, and maybe use that to optimize the fleet or use that to train our data. So if we translate these needs into the technical, or these business needs into the technical requirements, we need the horizontal scalability, massive scale, low latency, and high throughput. And this is a perfect fit for Cloud BigTable, our massively scalable, high throughput, globally distributed NoSQL database service. And this is the same technology that powers a range of billion-user Google services. We've proven this to work in Search, Maps, and Gmail. And these are applications that are getting millions of database accesses per second, and it's all happening with low latency. And if you're thinking a million QPS is a slow day for you, then you can just increase the performance by adding more Cloud BigTable nodes. Throughput will scale linearly based on the number of nodes. So 30,000 QPS for 3 nodes or 3 million QPS for 300 nodes. Based on your performance and cost requirements, you can easily scale with no downtime. You don't have to make a sacrifice for consistent throughput or latency as your data size grows. So we're going to take a look at 2 examples here. It's examples of fleet monitoring I've had a chance to work with that I think are pretty cool. The first, we're going to use the standard BigTable API, and then the other, we'll use the open source Geo Mesa API. So Cloud BigTable provides a ton of raw, speed, and scale, but does it come with a trade-off? This is a NoSQL solution, and with that, there's a very minimal query interface. You can do row-level lookups or row-range scans, and so you must create a row key that's going to group data together based on the kinds of queries you want to run. For this example, we're looking at monitoring the New York City bus system, and we want to focus on individual bus lines over time. So we're going to create a key that's a concatenation of the bus line, the timestamp rounded down to the hour, and then the vehicle ID. And for every data point within that hour, we can store them in the same row using BigTable's versioning feature. So with that, when we perform a get row, we're going to get all the information for a vehicle over the hour. And you can see it kind of going across Central Park. But more commonly, we'd probably use a scan. And here we're getting the entire data set for this M86 select service bus line. And looking at the heat map, we can already get a bit of data. We can see where the starts and stops of the bus are and maybe if there are any slow points. But if we want to get even more information, we could just we could change our query to have the bus line and maybe the timestamp rounded up to the month, and then see if that changes over time. And we've got we have a code lab with all of this data that works with the BigTable API, and we'll have a link for that at the end if you want to play around with this a little bit more. So now we've seen the Cloud BigTable API, but BigTable also has Apache HBase API compatibility. So you get to use that API if you're more familiar with HBase. And more importantly, this opens up a ton of additional capabilities for streaming, time series analysis, and geospatial analysis. For some of these, the additional API will set up this row key-based schema in a way that will maximize Cloud BigTable speed, so you don't have to do that. So we're going to take a look at Geo Mesa. And this creates a row key using the latitude, longitude, and timestamp to allow for performant geospatial queries. To use it, we change our dataflow job to write features using the Geo Mesa API, and then we're able to perform more sophisticated queries easily. Here, I've got a query that's selecting a bounding box on a map and a time frame, and I'm able to do this with just a few lines of code. So Daniel and I worked with this team at Google that would put air quality sensors in the back of Google Street View cars. And we were able to stream their data through our standard IoT pipeline and set up our dataflow job to write to BigTable using the Geo Mesa API. We were able to create a speedy dashboard to view the cars as they drove around San Francisco in real time and view batch process in 3 years of historical data. So we're seeing some of that historical data now. And these are just some of the ways you can use Cloud BigTable as part of your IoT pipeline. Now we're going to take a look at one more IoT scenario and a database to help out with it. Here, we've got another large-scale organization that wants to create public transit cards. So users can tap their card on the transit entrance, which will remove money from their card and let them enter. And then if they run out, they'll have to go and refill that. So this is a combination of these IoT use cases. We've got complex logic in here, and this is also very ingestion intensive. So for the technical requirements for this, we need a horizontally scalable system to handle this massive scale of a public transit system. We need high availability, so no one's going to have an issue trying to get to their train. And most importantly, we need strong consistency, since we're dealing with monetary transactions. And Google's offering of Cloud Spanner is a great fit for these. It's the first horizontally scalable, strongly consistent relational database service. Daniel spoke a bit earlier about consistency, availability, partition tolerance, as some of the things you might have to choose between when picking a database. And with most databases, you can only have two. But Cloud Spanner uses special hardware to allow for all three. And Cloud Spanner scales similarly per node, like Cloud BigTable. However, to support transactions with strong consistency, writes are going to be more computationally expensive than writes without strong consistency. Since BigTable doesn't have strong consistency amongst rows. So Cloud Spanner can provide up to 2,000 QPS of writes, whereas BigTable can provide up to 10,000 QPS per writes. But really, strong consistency is why that might be a deciding factor of using Spanner over BigTable. When you do decide to go with Cloud Spanner, though, you get the benefits of a relational and non-relational database. On the relational side, you get structure, schema, and enforced data types, as well as ACID transactions across rows, regions, and continents. And on the non-relational side, you get the horizontal scalability of a NoSQL database. If you're used to using a single node solution with a master replica setup, when that system needs a software update, security patch, or any kind of maintenance, you may have to take that system down and have your users experience downtime. We know your users and your services can't have scheduled or unscheduled downtime. So because Spanner is distributed, we can move your data around to perform routine maintenance under the hood without any visible changes to you or your users. So let's take a look at how we might use Spanner for this public transit example. We'll define a table that, with using schema, that should be pretty familiar to any SQL users. And then we can easily update the schema with no downtime. Here, we're creating a table of commuters and their card balances. When we want to perform a transaction on this, we can first get the balance, then check it meets the condition of being greater than the cost of the fare, and then deduct the cost of the fare from the balance. We've now taken a look at 3 IoT scenarios and found databases with particular strengths that complement the needs of these applications. But these examples could generate massive amounts of data. So how do you perform analytics across these ever-increasing data sets? And Daniel's got the answer for that.
Thank you. So we usually divide databases into OLTP or OLAP systems. Analytical queries usually need to scan over huge number of records and calculate aggregate statistics, whereas transactional queries usually touches a small number of records fetched by key. Our go-to solution for ad hoc analytical workloads is BigQuery. So anyone in here familiar with BigQuery? Cool. So before we do anything else, let's do a super quick BigQuery demo. Can we switch back to the... Thank you. So here we have one of the public data sets that are published through BigQuery. It's all the taxi trips in New York. Well, there's several years, but this particular year is 2015. And here you can see the different fields that we have and their data types. So I'm just going to do a let's say I'm a data scientist at the city of New York, and I want to just calculate the number of taxi trips per month during this year. So this is how I would do that. I'll use a Timestep function that will, I mean, it will focus in with granularity on, this is the timestamp and this the granularity. So we want to pick month from the timestamp, and then we just count the number of trips, and then we group it by month. So let's run this query. This is not a very big query. It's probably like around 150 million records. And here you see that you get, it's roughly around 12 million, 13 million taxi trips per month. And if you want to visualize this, it's super simple. Everything is a click away by just importing the data into Data Studio. So can we go back to the presentation? Thanks. So BigQuery is serverless. The underlying infrastructure is being seamlessly managed for you. You just upload your data to BigQuery or stream it into BigQuery, and BigQuery then provides you with a standards-compliant SQL interface, and off you go. It also comes with built-in support for geospatial and machine learning capabilities. Even those capabilities are expressed through SQL. BigQuery also has a new feature called BI Engine, which is a fast in-memory analysis service. Traditionally, when you use BigQuery, you get stable response times between 3 to 5 seconds, regardless almost of how much data your query is processing. But so 3 to 5 seconds, that's great for a data scientist. But for a dashboard, it could be a little bit much. So that's what for a dashboard, we might want to have sub-second latency, and that's what BI Engine gives us.
All right, thanks, Daniel. So today, our intention isn't to give you all the answers. We want to empower you to know how to choose a storage system. So we looked at complex logic applications, data ingestion intensive applications, and Daniel just showed us how to perform basically analytics on all of those. So take this knowledge and use it to make an informed decision. Don't treat storage as an afterthought. Thank you.
Billy and I will be around if you want to chat with us or about this or any other storage-related topics.
Yeah.
Thanks.